So feel free to ask questions or make comments whenever. So we'll start with just like the science behind ultrasounds. Um, so I think the word ultrasound is pretty, it almost gives away exactly what ultrasound is. So what does, like, if we break ultrasound into ultra and sound, what does the word ultra, what might ultra suggest and what might sound suggest? Do you guys have any ideas? A lot of sound. That is, yeah, that is a really neat way to put it. But yeah, Anna, that's basically what ultrasound is so ultra, if you take the prefix, it means beyond, extremely, so basically a lot. And then sound, it's just like a wave, and it's if we define it more formally, it's a mechanical disturbance that propagates through a medium. And the medium can be a bunch of different things. It can be air, it can be your body in the case of ultrasound. So yeah, that's basically sound. And it's really important to understand frequency when it comes to sound and ultrasound. So I'm not sure if you guys have learned this actually, but waves basically have different types of properties. So there's the wavelength, which is this dark purple one, and there's the trough and the amplitude, and there's the crest of a wave. But the most important term that we have to keep in mind for ultrasound is basically just frequency. And frequency is the number of waves that pass a fixed point per second. Well, it doesn't have to necessarily be per second, but that's what we use to kind of standardize it and to measure it. And the units for frequency is hertz, or Hz. And it basically is just like how many wavelengths, almost, if you were to map all of the sound out, how many wavelengths are there in that 1 second? Or if you were to just measure out the waves that are produced by a sound, or any type of wave, and then just see how many waves, complete waves, fit into that 1 second, then you're able to get the frequency. Are we so far so good? Feel free to put a thumbs up. I think there's that feature in the participants thing. Yeah, cool. Thanks. I appreciate it, Ethan and Hannah. Okay, so that leads us to what an ultrasound is, and there's really only one important part in an ultrasound, and that's the probe. I don't know if you guys can see my mouse, but this is the probe right here. It's a little like gray kind of handle that comes out of an ultrasound machine. And essentially what happens is that probe transmits high energy sound pulses, and they're 1 to 5 megahertz. And to give you an idea of how fast that frequency is, humans can only hear between 0.0002 to 0.02 megahertz. So this is a really, really high like frequency that we definitely cannot hear. And when this probe transmits those energy sound pulses, or like the wave, it'll basically travel into your body, and then it'll hit boundaries in your wave, or it'll hit boundaries in your body. And some of the sound waves can be reflected back, just like if you were to shout in like an alley, like there's an echo. So some of the sound waves will actually hit parts of your body and bounce back to the probe, but other parts might be more absorbed. So for instance, if you are underwater, if you're trying to talk, it's not going to travel as far. Whereas if you're talking to someone in air, like, or just in the atmosphere, it would travel a lot farther. You can shout and it'd travel a lot farther compared to water. So basically different mediums will absorb more or less of the sound wave, and there'll be less reflected back. And the calculations that occur in this ultrasound machine is basically calculating the distance between the probe and that tissue where it reflected off of. So this is a GIF or a GIF that kind of visualizes what an ultrasound does. So you can kind of imagine like this, I don't know, this blue matter as like the ultrasound, but basically when these waves are teal, that's like what the ultrasound probe is sending. And then when they're reflected, it's that like dark blue thing coming back to the probe, and that probe will just receive that and turn it into an image. And also this, oh yeah, this little, what do you call a spectrum, kind of shows where ultrasound is. It's not quite as high as other types of imaging, but yeah, even animals won't be able to hear ultrasound. So it's not going to affect like a dog or a cat, which have a lot better hearing than us. And yeah, and it's definitely a lot higher than what we can hear. Okay, so this is just like a really, really short video on how ultrasound works. I think it's like just a minute long, but I'm gonna skip the introduction. Let me share sound too. Are you guys able to see this? Can you guys see this? I just did full screen, so I'm not sure if you guys can.
Yes.
Okay, cool.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Yeah, so I think this is a cool video because it kind of animates what it looks like when you're sending and receiving like the little ultrasound and sound pulses. So, oh dear. Okay. Yeah, so going more in depth into just what ultrasound imaging would look like, this is what a usual machine would look like. But something also to keep in mind is that ultrasound, one of its most attractive aspects is that it's extremely accessible. So people have developed ultrasound machines that are literally just like a tablet, maybe like 1.5 feet big, and you can transport it anywhere. In fact, there have been researchers who will just like ask people in the parking lot of like a grocery store and do ultrasounds with people. So it can be extremely accessible. It doesn't always look like this ginormous machine here that is like very bulky, but this is just what a ultrasound that has really high frequencies would look like. So the more high frequency, you're able to see like usually better resolution, but we'll get into that a little bit later. So yeah, these are just the parts of an ultrasound. Has anyone ever had an ultrasound before? I'm sure a lot of us got ultrasounds while we were still in the womb, but have you guys seen those before? Yeah, Skylar?
I got an ultrasound once when I had pneumonia.
Oh, really? What did you get an ultrasound of?
I don't know.
Like where on, do you know where
Like,
on your body
oh
this
yeah,
is
my
at?
chest.
Your chest? Did the ultrasound machine look something like this or no?
I forgot because I was only 7.
You're only 7, yeah. So that's interesting, but I never knew they'd take it for pneumonia. So it's probably your lungs they were looking at then? That's cool. Yeah, I actually have gotten an ultrasound recently when I was at the lab, but I'll show you guys that at the end. But yeah, these are the parts of an ultrasound. So like you saw in the video, there's this transducer, I think it's one of these three things, and they have this really expensive but cool crystal at the end that basically helps emit and detect the sound pulses and echoes. And then the other part, if you see, is there's always a display screen because ultrasound is like real time. When you're put in ultrasound, if my hand is like the transducer, if you put it on your hand, it'll produce an image right away because it's already sending the sound pulses. So you want a display screen, and at the same time, this CPU or this computer processing unit is also calculating at that exact time to see to display like the density or like the colors or the shades on the image. So that's where all the processing happens, and there's literally like a very small delay from like real time and the image on the screen because technology has improved so much. And the last part of an ultrasound, not all ultrasounds have this, but usually the ones that you use in like a hospital will have these transducer pulse controls, and they just let you change like the amplitude or the frequency or the duration of the pulses. Like we talked about earlier, like the different properties of the sound wave or a wave. These little knobs basically just let you kind of alter the sound waves until it looks, get a sound wave to your liking. So this is just what an ultrasound tech looks like. I hope you guys don't ever have to encounter using an ultrasound for a medical diagnosis. Yeah, hopefully you guys don't ever have to get a medical imaging for, yeah, because it's probably not a good sign. But unless you're having a baby, then that's when ultrasound is used a lot. And yeah. Okay, so this is basically what happens during an ultrasound. I'm not sure if Skylar remembers this, but usually when you're getting an ultrasound, they'll apply this gel-like substance. It's clear and it's water-based. Do you guys have a guess of what this gel base is for? Like, why would technicians have to apply this gel to the skin and then put the transducer?
I'm pretty sure that very loud sound can break things, so they use that gel to protect the body.
To protect the body? That's a really
Or the baby.
Or the baby, yeah, that's a really good. I think that's really similar to what. Yeah, I think that's basically what it. It's a little bit off from the actual use, but it's pretty close. So these gels are basically to kind of provide an insulation. If you surround the entire transducer with this gel, then it'll hit that gel for sure because it's like covering the transducer. But if you were just to put a transducer onto your skin, there might be some air holes, and that can create discrepancies in the image. Yeah, exactly, Yifan. The image will be a lot clearer if you use this gel. And it's basically just, yeah, it's just like a water-based gel. And then after the technician puts the gel on the area that they want to scan, they'll just cover the probe with a plastic cover for sanitation purposes. And then they'll move the probe along the skin that's gelled to get the image that they desire. And usually you'll notice, yeah, that's exactly right, Yifan. So usually you'll notice that when you're getting an ultrasound, they'll kind of like put it exactly or around where you want to image, and they'll just move it around a little bit because ultrasound produces like a live image. So usually you never just hold it there unless there's something really interesting or concerning. Usually the ultrasound just be kind of moved back and forth. And sometimes people also do that to get a 3D image. So for instance, you can actually, if moms want to see like a 3D image of their baby, they can use ultrasound to basically take a bunch of images and then produce like a 3D model of their baby in the womb. It's pretty cool, but yeah, it's insane how much ultrasound has developed. So yeah, it just, once again, the gel is really important to seal any of the air pockets. And there are many different applications for ultrasound, but these are the main four. So the first one is obstetrics, and I'm sure this is the one that we're all familiar with, or the one we associate ultrasound to, and that is basically imaging a fetus in the womb. And the purpose of using ultrasound is that you can see like the size, and using this ultrasound, you can determine the position of the baby. Is that dangerous to the mom and the baby? And you can guess like, or just estimate the due date and the age of the baby. Because ultrasound is really, really specific in measurements. You can see basically how big everything is down to the millimeter. So ultrasound is really useful for that. And the very important part about ultrasound is sound waves don't have radiation. It's just sound basically at a really, really high frequency. So that's why there's not really any side effects. There's no radiation when you use ultrasound. So that's why we use it for babies, which are really, really delicate. And then the second one is to see inside the heart, or cardiology. And using ultrasound, you can look at the way that the blood flows. So when blood is flowing in the ultrasound, it actually kind of creates just like minor disturbances, so that when you're sending those pulses, you can actually see the way that the blood is flowing. And sometimes ultrasound can even be used if your blood vessel is close to the top of the skin. It can be used to see if there's like any clots or just like fat or plaque buildup in your major blood vessels, which could possibly cause a stroke. So those are very important parts of ultrasound and can definitely help save lives. And then the third one, this is an area that's developing a lot, which is urology, and that's just imaging of our kidneys. Once again, it's to look at blood flow and also possible cancers and diseases. A really common thing in kidneys is called fatty. Oh, no, just kidding. That's fatty liver. But you also want to look for kidney stones, because those can be definitely a hazard. So that's urology. And then the last one, it's just kind of general. Sonography is like the umbrella term for using ultrasound to diagnose diseases, cancer, and also to look at blood flow. So those are just like the four main ultrasound uses. They're pretty, I guess, like self-explanatory. Like you already know that ultrasound is used to look at babies and to look at different parts of our body, but those are just specific areas where ultrasound has been really refined in. And this is, I think, the coolest part is learning how to read an ultrasound. So ultrasound is pretty straightforward when you look at imaging, because the color that shows up, or the shade of gray that shows up on an ultrasound image, is extremely dependent on the substance in the body. So the general pattern is that bone is always like bright white, and your bone, like if you've seen a bone in real life, but it's just a really hard surface. And as a result, if you're to send like a ultrasound pulse to it, a bone, it's just going to reflect right off, and none of it is going to go through. So usually you can identify a bone in an ultrasound as like this, you see this like white section, and underneath that white section is just, there's no image. There's like a shadow, they call it. And that's because once that ultrasound pulse reaches the bone, it can't penetrate the bone. It just reflects right off, creating a really, really bright image. And since it can't go through or permeate the bone, there's no imaging below it or past that bone. So that's how you can determine if there's bone in an ultrasound image. But then as we get darker and darker, that just means we're getting into less and less dense substances. So yeah, the denser the tissue, the brighter the image. And I think if you kind of just imagine like talking to or trying to shout into a wall, the denser the wall, the louder the echo. But if you're talking to, I don't know, like a wall that's like slimy or just not as dense and solidified, it's not going to echo as much. And as a result, you won't get much of a reflection back, and the transducer won't pick up as much of signals. And so your image for that little section is going to be darker because there's not as much signal coming back. So another way to think about it is that sound waves travel easily through fluid, and because they travel so easily, they're not going to reflect much back and therefore create a dark image. whereas bone, once again, really reflective. Muscles, pretty reflective because they're pretty dense. Those are highly reflective, and they'll create a light image because they'll just bounce off right back to the transducer. And the transducer, given the time in between that it takes to reach that substance and then come back to the transducer, and the transducer can use that time to determine like the substance's distance and also the color that it'll produce. I feel like I just like lectured on, and that makes sense to you guys. Feel free to ask questions or clarifications. Are we all good? Okay, let's look at some examples. So let's just guess the substance. Your three choices will be at the top. So your three choices are muscle, fluid, and bone. And so you're just trying to guess what this blue star here is. What type of substance is right there? Muscle, fluid, or bone? Feel free to put it in chat what your guys' guesses are. Muscle? You got two guesses for muscle. Three guesses for muscle. Anyone want to be a devil's advocate and guess something else? So the region that this star is pointing at is this like entire dark area. But notice some characteristics like this bright white line up here, and usually, yeah, like complete darkness, like this pitch black, is usually very indicative that either it's a shadow or it's fluid. Skylar said fluid. Does anybody want to guess anything else? Okay. So it's actually, nobody actually got it, but it's actually bone. And it's pretty difficult given that you don't know where exactly we're looking at. You don't have any type of, yeah, you guys don't have any background of what this image even is. But some little tips that you can use to kind of identify this is you'll notice that there's like this white, there's this white line outside of it, and it's extremely bright, especially right here. So that tells us that it's a really reflective area. And then beneath it, you almost don't get any signal at all. So usually in these ultrasound images, let me turn on a laser point. Up here is like surface level, or like the skin or whatever the closest thing to the transducer is. And then down here is the furthest away from the transducer. So this shows that as we're getting further away, or after we hit this white thing, it's like completely a dark shadow. And you know it's not liquid because, or fluid, because there's this white surrounding. And fluid usually will never have that. It'll just be a blob of darkness. So this, yeah, the characteristic of bone is to just look for this little bright light, bright kind of outline. And you guys are obviously not ultrasound, I forget the word for ultrasound specialists, but you guys definitely don't exactly know. So there's no shame in guessing wrong, because yeah, I couldn't tell you either before this. All right, so now we've crossed off, well, maybe there might be repeats, but what do you guys think this is? Where do you think this blue star is? Muscle, fluid, or bone? All right, we gotta vote for muscle, 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 muscle. Yeah, that is exactly right. It's muscle. And it's relatively dark, but it also has its light areas. But the main giveaway is like you can see the fibers in this, like the strands of fibers of this muscle. So if you guys have ever taken a human anatomy class or seen pictures or diagrams of muscle, you'll notice that it just looks like these little strands that are just like tensed together, or they're pulled together. And that's basically like an indication of muscle or tendons, but usually this is muscle. You guys didn't have the option for tendon. And then this is the last one. So where's this star at? Muscle, fluid, or bone? Fluid. Yeah, that is exactly right. So I think it's really easy to get it's easy to get bone and fluid mixed up because this one there's also like there's also this bright white part surrounding it, you know, like wouldn't couldn't that also signify that it's a muscle or that it's a bone? But the main giveaway is that even beneath this, the reason why we know that it's not a bone is that even below this dark area, there's not a shadow. We can still get imaging beneath it and it's really relatively clear. So that tells us that it's fluid because it's able to move through and still give us an image, and it's not a shadow. And only bones produce shadows, so therefore it's a fluid. And this really dark area just shows that the fluid is really not very dense. And you can also see little specks in it, which is not what you would see in a shadow from a bone. And once again, there's just such good imaging beneath it, so it definitely cannot be a bone. And obviously having context of what exactly this image is will definitely help you determine whether it's a bone, a muscle, or if it's fluid. But yeah, this is kind of just a little application of the three, like the different shades and what it looks like. All right, so now that you guys can identify the different substances in your body, we're going to kind of advance to trying to guess the different body parts, and it gets progressively more difficult. And I'll just say this before we get started. Ultrasound is definitely not known for its high resolution. That's not what ultrasound is known for. It's known to be accessible and accessible, relatively affordable, and you can get it real time, and there's no radiation. So high resolution is not one of ultrasound's selling points, but this one should be pretty easy. What do you guys think this part of the body is, or what is this image of? Feel free to put your guesses in chat. I'm pretty sure you guys are going to get this one. Yeah. It is the womb or a fetus. So this is the part of obstetrics. That's the part of, that's like the method of using ultrasound to image the womb or fetus. But yeah, it's the womb. And it's pretty cool because you can see like right here, it's like the little bone that's developing. And you can already see a little bit of the brain. We'll talk more about brain and MRI, because I think that's probably the coolest application of MRI is the brain. But you can tell that there's not that much like contrast in the brain because it's still developing. You can't really take an ultrasound of brains anymore because our brains are so much bigger now, but if you were to take an ultrasound of our brain right now, you definitely see a lot more contrast. It wouldn't just look like a blob that's almost the same shade throughout. But yeah, that is the fetus. And going back to obstetrics, if we were to actually get this image, you'd be able to actually measure exactly how long the baby is from like here to here, or from how big its head is. And that basically allows technicians or doctors to give a prediction of when the baby's due date is, or how old the baby is, how many weeks old it is. All right, here's another one. I thought this would be a lot more difficult if it wasn't animated, so hopefully like the movement or just movement of this image can give you guys a hint of what body part this is. Nice, Lydia. It's exactly right. We got lungs and we got heart. Got 3 heart. Anybody else want to take a shot? Yeah, it's the heart. So here we can see the ventricles and the arteries. And this is once again going back to the point that ultrasound, when you do an ultrasound, it can kind of distort what it looks like, because when you send waves from the transducer, the waves are going to go, sound waves are going to just go all in all directions. So your image might be a little bit warped and it's not the clearest. This honestly just looks like 4 black areas just moving and expanding. It doesn't look like a heart, but these 4 areas are just the ventricles and the arteries. So we have like the right ventricle and the left ventricle and the right artery and the left artery. And yeah, there's really not much that gives it away. If you had been studying ultrasound for a while, you'd know by heart that this is the heart. And also the image kind of movement is like the pulsing of a heart. But another thing you can kind of notice is that this is fluid, so it's probably blood. So that's what we're mostly made up of. And the heart has 4 main compartments. And if you knew that, if you had some background in heart anatomy, you might be able to tell. But yeah, I think it's the movement that kind of gives it away. But if you were to scan your heart, like right here, put an ultrasound right here and scan the heart with an ultrasound, you'd be able to see the beating like live, which is really cool. Oh yeah, here's the, oh, I got it wrong. Yeah, it's right ventricle, left ventricle, right artery, left artery, because you kind of have to imagine the heart as if that heart is yours. You have to flip it. But yeah, this is just a little diagram of the different compartments, the 4 main compartments in a heart. And something really cool, you can't really tell from this image, but a feature of ultrasound is that you can actually see which way the blood is flowing or pumping. You have to use special like techniques, and there's a special technology that you have to use in the ultrasound, but you can tell which way the blood in the heart is pumping, and it's almost always going to be the right direction. All right, this is a very obscure image, so yeah, give this your best shot, guys. I don't know. I don't think I would be able to get this. When I first saw this image, I was a little bit baffled at first. But take a shot at what you guys think this image is, what this image is of. Skin, good guess. Anybody else? I mean, this is, you can see this like dark area, fingers. One thing about fingers, if you were to scan your finger, you probably see like a bone layer, and I don't know if your bone looks exactly like this. Any other guesses, guys? I want someone to get it. I will say someone has guessed it before. So if you look in the chat before, it's public too. Someone has guessed it. Yeah, nice, Skylar. It's actually the lungs. And once again, very obscure because it's like this is one of your lungs and this is the other lung, but the image is not very good. But this is the lungs. You can kind of see the dark shapes of the lungs in there, but yeah, since it's air, the sound just can travel through it really, really easily. It's not going to be reflected or anything, so that's why you just get these super dark, ominous areas for your lungs. But yeah, these are your lungs. What's at the thing at the top of them? This is probably just other tissue in your body. Oh, you mean up here? Which part do you find? Yeah, this dark area. I'm honestly not sure. Because to get this image, you'd have to use probably one ultrasound transducer and just scan it completely across. So there's no ultrasound image that you can get your entire lungs in at once. So I'm not actually sure what this area is up here. And Also, something you can think about is like slices, I guess. If this ultrasound is like on your chest, how deep it's going so that you only get the lungs and you don't get like the heart in it and other parts like your esophagus. Those parts aren't shown in this. So this might be like either, I think it'd probably be like either the lower parts. If you were to lie down, like let's say someone's lying down like this, this might be an image of their lungs like at the more towards the back of their body or maybe towards the front so you don't get any other organs in it. But yeah, this is definitely a really interesting image. All right. I don't even know if you can even see the organ in here, but take a shot at what this one is. What do you guys think this is an image of? Kidney, liver? Yes, it is an image of a certain organ. You're correct, Alvin. Stomach? Yeah. Once again, if you are a trained ultrasound specialist, you'd be able to see the kind of overall shape and be like, wow, that is exactly that. But yeah, it's quite difficult without knowing the context of an image. So it is the liver. It's very, very obscure. I feel like it's really difficult to see. This is a healthy liver. Actually, let me show you guys. Fatty liver. So this is a healthy liver. It looks, there are certain characteristics of a fatty or unhealthy liver and a healthy liver, but a fatty liver is definitely problematic. So yeah, here's a fatty liver. A normal liver, it's going to have like little fluid holes and stuff, but a fatty liver, this is not a very good example. Let's see, are there any good images? Yeah, fatty liver will just, a fatty liver has certain characteristics. None of these actually, I feel like, show it well. But normal liver, you kind of want to look for this consistent kind of shade throughout. But fatty liver, you will see, I don't know the medical term, guys. I've seen some images, but that is definitely not normal. But you could definitely look into this yourself if you want to. But yeah, this is the liver, and you can kind of see the shape like this. That is the liver area. So yeah, just to kind of conclude that little section, ultrasound can definitely be extremely, yeah, it's not the most precise imaging tool out there. But yeah, the pros, and there's many, many pros. And the first one is that it's generally painless. I don't know when you'd actually experience pain in an ultrasound. Maybe if the gel is really cold to you, or if the technician is applying pressure, trying to get a better image. It's pretty painless. And the second is that there's no ionizing radiation. We're not sending radioactive pulses into you or just sending sound pulses into you. So it's not going to have radiation effects. And another very good pro is that soft tissues are easily imaged because they are darker and will have more contrast because they'll have varying density. So you'll be able to see the textures like we kind of saw in the muscle. You'll be able to see like the fibers. And I think this is the most important, these are like the most important parts of ultrasound. It's that it's extremely accessible, portable, and less expensive. So if you guys remember on that one slide where we saw like an actual ultrasound like device, you can roll it around, and that one was actually one of the less portable ones. But ultrasound is relatively affordable. It's the cheapest of all the types of imaging out there. And because it's so affordable and you can basically adjust the ultrasound to make it into like a small, like almost like a laptop sized ultrasound with just a probe coming out, you can make them into really accessible gadgets that can be sent out to underprivileged areas without much of a high cost. And it'll also make it much more accessible to people so they don't have to go to necessarily a hospital and book an appointment. They can just find someone with these ultrasounds. In fact, there's actually an ultrasound app. I actually recently learned about this, but you can actually just take your phone and download this app, and you'll just get like this add-in, and you'll plug it into your phone, and you can do little ultrasound images through that. I'm not sure what it's called, but that exists out there. So if you want to ultrasound, if you want to have your own ultrasound, you can also invest in one that just uses your phone, a phone app. So there's also that. But there's also some cons. And like I mentioned before, ultrasound is not known for its high resolution, and bones can't be easily imaged because they're so reflective and they create shadows that you basically can't get any details on bones in an ultrasound. And this is really, really, really minimal. It can maybe cause a little bit of an increased temperature in your tissues, but it's so minimal that there's no side effect. That's just if we're being really, really picky. So the really only two downsides of ultrasound is that it's lower resolution, it's pretty grainy, but I mean, at the same time, it's like a real-time image. And also bones cannot be imaged. So if you were to sprain, or if you were to injure your bone, you would not get an ultrasound, you get an x-ray for that. So yeah, this is just an overview of what it is. They're created by transmission and reflection of extremely fast sound waves, or ultra fast sound waves, ultrasound. And okay, there's a typo here. Bone shows up bright while tissue shows up dark, especially fluid shows up dark. And it can be used for diagnosis without threats of radiation, which is why it's really preferred for patients who might have already been exposed to a lot of radiation, or for young children. They're a lot more delicate, or even babies in wombs. So that's when ultrasound is the preferred method. And once again, this is the most important. I think it's extremely portable and accessible. So that's like the main selling point of ultrasound. That's why it's still here today. And I